Hi everyone, welcome to the video lectures on complex analysis. This video lecture includes introduction to complex numbers, their algebraic operations and geometric representation. Introduction. Complex analysis has many applications in heat conduction, fluid flow, electrostatics and in other areas. It extends the familiar real calculus to complex calculus by introducing complex numbers and functions. While many ideas carry over from calculus to complex analysis, there is a marked difference between the two. For example, analytic functions, which are good functions of complex analysis, have derivatives of all orders. Analytic functions are good functions in the sense that they are differentiable in some domain. Thus, in certain ways, problems that are difficult to solve in real calculus may be much easier to solve in complex analysis. Some applications of complex analysis in applied mathematics. Two-dimensional potential problems can be modeled and solved by methods of analytic functions. Many difficult integrals, real or complex, that appear in applications can be solved quite elegantly by complex integration. Most functions in engineering mathematics are analytic functions, and their study as functions of a complex variable leads to a deeper understanding of their properties. Before studying complex numbers, we have to understand what is a complex number. In your school classes, you have already studied a complex number as a number of the form z equal to a plus ab, where a and b are real numbers and I is equal to square root of minus 1. This definition may not give an exact idea of what a complex number is. Here we are going to see a complex number as an extension of real numbers. So first we consider complex numbers, their geometric representation and algebra of complex numbers. Consider certain real numbers, for example, the real number 1.5, 2, 3.65, minus 2.5, etc. And how to represent all these real numbers in a number line? So this number line having midpoint 0, and we are representing all these numbers, real numbers 1.5, 2, 3.65, minus 2.5, etc. by measuring the distance from the midpoint, say 0. For positive numbers, we are measuring the distance to the right of 0, and for negative numbers, we are measuring the distance from 0 to the left hand side. For example, we can mark this 1.5, suppose this is our 1.5 and this is our 2, 3.65 and minus 2.5, etc. That means in real number system, we are plotting or we are representing every real number in a number line geometrically. Next, we are going to define what is a complex number. For defining complex number, we are considering two perpendicular axes. One axis is called the real axis and another is called the imaginary axis. These are our usual x-axis and y-axis. In this two-dimensional coordinate system, we take an ordered pair xy and we call this as z. And this ordered pair xy designated by the letter z is called a complex number. So a complex number is an ordered pair xy where these x and y are real numbers. And this is written as z is equal to x plus iy. And what is I? This I is the coordinate 0, 1. So I stands for I is equal to the pair 0, 1. And we can see that this xy plane or this coordinate plane contains all ordered pairs of the form x comma y. And every ordered pair xy in this plane is called a complex number. And in particular, whenever this y coordinate is 0, the numbers lying on the x-axis or the real axis, they are called our usual real numbers. For example, suppose we are considering a number of the form 2, 0 that will lie on the real axis. And if you are considering a number with its first part, that means x coordinate is 0, that is lying on the imaginary axis. And one more notation, in this representation, z is equal to ordered by x comma y or z is equal to x plus iy. This x is called the real part of the complex number z and y is called the imaginary part of the complex number z. And we can see that all the real numbers lying or all the real numbers are subset of this complex numbers. Collection of all real numbers is denoted by capital R, and the collection of all complex numbers is denoted by capital C. And we can see that these real numbers are subset of complex numbers, because the real numbers which are lying on this real axis or x axis are obtained by putting the corresponding y coordinate or the imaginary part of z is equal to 0. So that is a special case of complex number as real numbers. Algebra of complex numbers. So we have defined a complex number z as an ordered pair xy, or a representation of the form z is equal to x plus iy. So let us take two complex numbers. So the first algebra is called the equality. So let us take two complex numbers. Z1 is equal to x1 y1 and z2 is equal to x2 y2. Z1 equal to Z2 implies Z1 equal to Z2 if and only if the pair x1 y1 equal to the pair x2 y2, and because they are coordinates, so this is if and only if x1 equal to x2 and y1 equal to y2. So this is called equality of two complex numbers. That means whenever two complex numbers z1 and z2 are equal, their real parts are equal and their imaginary parts are equal. So first we define addition of complex numbers. Again we are considering two complex numbers. Say z1 is equal to x1 y1, z2 is equal to x2 y2, and these two complex numbers are added. That means z1 plus z2 is equal to x1 y1 plus x2 y2, and this addition is defined as x1 plus x2 comma y1 plus y2. So that means whenever we are adding two complex numbers x1 y1 and x2 y2, we are adding their real part separately, take it as the new real part, and imaginary part separately, take it as the new imaginary part. So sum of two complex numbers is again another complex number with the real part equal to sum of the real parts and imaginary part is equal to sum of the imaginary parts. See the definition of multiplication for two complex numbers. Say z1 is equal to x1 y1 and z2 is equal to x2 y2. Their product z1 z2 is defined as x1 y1 into x2 y2 is equal to, so the product is defined as a new complex number with real part is equal to x1 x2 minus y1 y2. That means multiplying the real parts x1 x2 minus then product of imaginary parts. So that is taken as the new real part, and imaginary part is x1 y2 plus x2 y1. That means we are mixing the real and imaginary parts of first and second complex numbers together and adding. So this is a definition of multiplication of complex numbers. So now from the definition of addition and multiplication of two complex numbers, we can deduce the corresponding operations for real numbers. That means suppose we are adding two real numbers x1 and x2, so the real number x1 can be taken as a complex number with the imaginary part is 0, so x1 0 plus another real number x2, that means the complex number x2 0. Now we are applying the basic definition of addition of two complex numbers. So how to add two complex numbers? For addition of two complex numbers, we are adding their real parts separately, that means x1 plus x2, and adding their imaginary part separately, so that is 0. And similarly for multiplication, suppose we are multiplying two real numbers x1 and x2, so we take the first real number x1 as a complex number, say x1 0 into x2 0. So x1 0 into x2 0, multiplication of two complex numbers means product of the real parts minus product of the imaginary parts, that is 0, that is taken as the new real part. And what will be the imaginary part? Imaginary part is the mixing of real part with the imaginary part of the other, and similarly for the second set, that is x1 into 0, x1 into 0, 0 plus 0 into x2, that is 0. So we have the result x1 is to 0, that is a real number. That means the operations of addition of complex numbers and multiplication of complex numbers are natural generalization of the ordinary operation of addition of two real numbers and multiplication of two real numbers, because from the definition of addition of complex numbers and multiplication of complex numbers, we can deduce the corresponding operations in real number system. That means x1 plus x2 or the product x1 x2 gives a result in the ordinary multiplication of real numbers. So we can treat the complex numbers as the natural generalization of real numbers. So hence we can write our x0, the complex number x0 means x, and 0y is equal to, what is 0y? 0y is equal to 0 1 into y. 0 1 into y. What is 0 1? 0 1 is I. So this is our iy. Or we can treat this product as product of two complex numbers iy. That is I means 0 1. 0 1 into y. Y is the real number. So we can write this as y comma 0. Applying the usual definition of multiplication in complex numbers. That is, hence we can write the complex number z is equal to x comma y is equal to x0 plus 0y. That is equal to x plus, instead of our 0y, we can write it as iy. That is, z is equal to x plus iy. So this will be our standard notation for a complex number. And we have studied that a complex number is a complex number z is an ordered pair xy, where x and y are real numbers, or we can represent that complex number in another convenient form as z is equal to x plus iy, where this I stands for the complex number 0 1, where this x comma y are real numbers and this I means the complex number 0 1. Hence we can see one more result. What about I square? I square means I into I, that is 0 1 into 0 1, 0 1 into 0 1, multiplication of two complex numbers. So the product is product of the real part minus product of the imaginary part, then product of real into imaginary, that is 0 into 1 0 plus 1 into 0 0. So that is equal to minus 1 comma 0, or this is the real number minus 1. That is, I square is equal to minus 1. So that is another fundamental result. Now see the another operation, subtraction of complex numbers. So z1 minus z2, z1 minus z2 is equal to x1 plus iy1 minus x2 plus iy2 is equal to, arranging real part and imaginary part separately, that is x1 minus x2 plus I into y1 minus y2. So this is the definition of subtraction of two complex numbers. So the difference of two complex numbers z1 and z2 is another complex number with the real part, difference of their respective real parts, that is x1 minus x2 plus I into difference of their imaginary parts. Next, to see the operation of division. Let the quotient of two complex numbers z1 and z2 with z2 not equal to 0 is denoted by z. And this on cross multiplication will give z into z2 is equal to z1. That implies, and what is z? Z is a general complex number. We take the general form as x plus iy. So x plus iy into z2, x2 plus iy2 is equal to x1 plus iy1. That means two complex numbers are equal. Two complex numbers are equal if and only if their real parts are equal and imaginary parts are equal. So from this we can construct two equations. One equation is x1 is equal to, that means the real part of the right hand side equal to real part of the left hand side. x1 is equal to xx2 minus yy2 equation number 1, and y1 is equal to xy2 plus yx2 equation number 2. So treating this as two algebraic equations in the variables x and y, we can solve for this x and y. So using the rule of cross multiplication, we have x divided by determinant x1 minus y2, y1 x2 is equal to minus y divided by determinant x1 x2, y1 y2 is equal to 1 divided by determinant x2 minus y2, y2 x2. So now the quotient z is equal to z1 by z2. What is the value of z? Z means x plus iy, that is equal to x1 x2 plus y1 y2 divided by x2 square plus y2 square, that is a real part, plus I into imaginary part becomes x2 y1 minus x1 y2 the whole divided by x2 square plus y2 square. In order to remember this computation of quotient, we will apply a technique. What is the technique? In order to compute this z1 by z2 where z2 not equal to 0, directly writing the values of z1 and z2, x1 plus I y1 divided by x2 plus I y2. For obtaining this result, we are multiplying both this numerator and denominator with another complex number, that is x1 plus I y1 into x2 minus I y2 divided by x2 plus I y2 into x2 minus I y2. Then after expanding this numerator and denominator, we can see that the same result will obtain. So, and separating real and imaginary parts, the real part is x1 x2 plus y1 y2 divided by x2 square plus y2 square plus I into imaginary part is x2 y1 minus x1 y2 the whole divided by x2 square plus y2 square. So this is the technique we will apply for computation of the quotient z1 by z2 whenever z2 is not equal to 0. Now see what is a complex plane. See, in the definition we have seen that every complex number is represented as an ordered pair xy, or we call it as z, where this x and y are real numbers. Suppose this is our complex number, say z is equal to x plus iy. Suppose we are reflecting this complex number about this real axis. So we get another complex number. If we take the reflection of the complex number xy or z about the real axis, we get another complex number with the x coordinate x and y coordinate minus y. And this new complex number is called the conjugate of the first complex number z, and we denote this by z bar. That is, if z is equal to x plus iy, then its conjugate z bar is equal to s minus iy is called the complex conjugate. And if you are adding together these two equations, what is the value of z plus z bar? Z plus z bar is equal to 2x, or x is equal to z plus z bar divided by 2, and subtracting we get z minus z bar is equal to y plus iy, that is 2iy, and we get y is equal to z minus z bar divided by 2y. That is, for an arbitrary complex number z is equal to x plus iy, its real part of z is equal to z plus z bar divided by 2, and imaginary part of z is equal to z minus z bar divided by 2i. So these are the simple properties of the operation conjugation. Z conjugate to the whole conjugate, the same complex number. That means if you are reflecting this complex number z bar or x minus y about this real axis, we get the same complex number. And z1 plus z2 conjugate is equal to z1 conjugate plus z2 conjugate, and similarly for quotient, z1 by z2 the whole conjugate equal to z1 conjugate divided by z2 conjugate. Now say the complex number z is equal to x plus iy, or the coordinate x comma y. That means this complex number z is represented in this complex plane by measuring two types of distance. One distance is from the imaginary axis, that is the x coordinate, and another distance is from the real axis, that is the y coordinate. And because we are in a Cartesian coordinate system, or the two-dimensional Cartesian coordinate system, we can represent this complex number z using another method, that is called the polar form. Suppose this is our origin. In polar coordinates, we can designate every Cartesian coordinates in two-dimensional plane by knowing two values. One value is from the distance from origin up to that point. Suppose this is our r, and another is by measuring the angle between the x-axis and the radius vector. So suppose this angle is theta. So we can represent the same complex number or the same Cartesian coordinate xy using another notation, that is called in terms of r and theta, where what is r? R is the distance from origin, that is origin has coordinates say 0 0, complex number 0, 0, and Z means it is the complex number x comma y. So what is R? R is the distance between 0, 0 and xy. So that is equal to square root of x square plus y square, and we will use the notation mod Z. Then from the right triangle, what is cos theta? Cos theta is equal to OA divided by OZ. What is OA? This OA is our x and AB is y. So that is cos theta is equal to OA divided by OB, that is x by r, or x is equal to r cos theta. And similarly sin theta is equal to opposite side, that is AB divided by OB, that is y by r, or y is equal to r sin theta. Therefore, the complex number Z is equal to x plus iy can be written in polar coordinates r and theta. What is x? X is equal to r cos theta plus I into r sin theta, where this r is a common factor, r into cos theta plus I sin theta, and this is called the polar form or modulus amplitude form or modulus argument form of the complex number Z is equal to x plus iy. And how to compute that theta? So in order to compute this theta, we are dividing this sin theta by cos theta, so we get tan theta. Tan theta is equal to y by r divided by x by r, so we get y by x, or theta is equal to tan inverse y by x. So that tan inverse y by x is an angle between 0 and 2 pi, or that angle theta plus an integral multiple of 2 pi. So this angle theta is equal to tan inverse y by x is called argument of Z or arg Z. And that is not a single valued expression theta. That theta may be, for example, suppose we are considering the complex number, for example, this is 1 plus I, this is the complex number 1 plus I, or the coordinate 1 1. Suppose this is the coordinate 1 1, then this distance is square root of 2, and what will be this inclination? This inclination will be tan inverse of 1, that is pi by 4. So that angle theta may be pi by 4 or pi by 4 plus 2 pi or pi by 4 plus 4 pi, etc. So this theta or argument of Z is not single valued. So in order to get that single valued expression for theta, that is called the principal value of the amplitude, we denote this by capital arg Z. Arg Z is equal to the value of theta lying between minus pi and plus pi, so including plus pi. So this completes the entire range, full rotation. So this is called the principal value of the amplitude or argument. Now we have to remember two more formulae, that is called the Euler's formula. Euler's formula is e raised to I theta is equal to cos theta plus I sin theta. So this is a complex number having modulus 1, because what is the modulus of this complex number? Square root of cos square theta plus sin square theta, that is 1. So, and another formula is De Moivre's theorem. What is De Moivre's theorem? Cos theta plus I sin theta, the whole raised to n is equal to cos n theta plus I sin n theta.